Four-step recipe in solving a problem with multiple forces acting. We got a net force that's made up of several different forces. Then we have to follow this four-step method, beginning with draw a free body diagram. A free body diagram is a diagram that shows what? All of the forces acting on an object. Good. All of the forces acting on an object. This could be a free body diagram of a person standing on the floor. Gravity is acting down, and the normal force is acting up. This could be the free body diagram of a box on a hill. We've got gravity acting down, and the normal force acting at 90 degrees right here. This could be a free body diagram of an object being pulled to the right and being pulled to the left, and the normal force and force of gravity. Draw a free body diagram. Show all of the forces, whatever they are, acting on the object. Now the second step, we take that free body diagram, look at all the forces that don't cancel out. Some of them will cancel, right? Gravity and the normal force don't always cancel, but they often do. Cancel them out, cross them off. The ones that don't cancel out, include them in step 2, which says F net is equal to the sum of the forces. If there's one force acting, that's it. F net is equal to F1. Good. If there's more than one force acting, maybe two forces, then F1 plus F2. Maybe there's a whole bunch more forces acting. Just keep adding terms for each force that's acting on the object. Step number 3, anybody remember? Not much of a step up from number 2. Yep.
Is the equation for force in of mass times acceleration?
Yes. So we're going to replace F net with M times A. It becomes MA is equal to F1 plus F2 plus whatever forces, whatever other forces we have there. And finally, step 4 is just sub in your numbers and solve. But what do you got to make sure of when you sub in your numbers and solve here? Make sure you include negatives, right? Positives and negatives. Don't worry about that until now. Okay, when you're writing down the equation, don't worry about negatives at all. But when you sub in your numbers, then you got to worry about negatives. We had a worksheet for homework last night, worksheet number 11, questions 1 to 6. I want to do 3 of those questions. I want to do 2, I want to do 5, and I want to do 6 with you right now. Question number 2 says a 4-kilogram box is being pulled to the right with a force of 50 newtons, but a force of friction of 25 newtons opposes the motion. Friction always opposes motion, doesn't it? What does it? What about friction between my foot and the ground? That's what allows me to run. Right? If there's no friction between my feet and the ground, or between my shoes and the ground, I can't run, can I? So that's not opposing motion, isn't it? Isn't that helping motion, contributing to motion? Well, kind of, but fundamentally it's still opposing motion. Why am I being propelled forward? Because of the lack of sliding or the lack of slipping between my feet and the ground. If there's motion between my feet and the ground, if my foot slides on the ground in this motion relative to the ground, I don't go anywhere, right? So friction, which resists the motion between my foot and the ground, actually allows me to be propelled forward. Friction always opposes motion. Even when it seems like it's helping something, it's helping because it's opposing motion. Does that make sense? So friction opposes motion, including in this case. Let's draw a diagram here. Step number 1. We've got a force of gravity acting down, and we have a normal force acting up. Now, since this object isn't accelerating up or down, those two forces are going to cancel out. They're going to balance out. So let's just cross them off. Okay, they're gone now. That's good, because that means we have less forces to deal with when we go to do the math. We have a force to the right of 50 newtons. I'm going to call that F1. You can call it FR if you want, the force to the right. You can call it FA for the applied force. Call it whatever you want. Call it FQ because you like the letter Q. Call it whatever you want. I don't care. I'm calling it F1. Now, friction's acting 25 newtons to oppose the motion. If it's in the, look at the diagram as it stands right now. Which way is it going to move? To the left or right? It's going to move to the right because that's the way the force is, right? If it moves to the right, friction's going to act to the left. So that means we got a force of friction here, F2. Let's just call it FF. Of 25.0 newtons to the left. Okay, there's step 1. Step 2, what was step 2 again? Yeah.
F net equals to F1 plus how many?
Right. And in this case, we have F1 plus, what's the other forces acting? Yeah, we'll call it FF though. I'm calling it FF. If you wanted to call it F2, you could. But friction is such a specific force that I usually call it FF rather than an F2. It doesn't really matter though. Now the net force, step 3, the net force is also equal to what in step 3? The net force, Jenna, is also equal to what in step 3? Yeah, mass times acceleration. So let's just replace F net with m times a is equal to F1 plus FF. And now let's step 4, just sub our numbers in here. M is 4.00 kilograms. A is what we're looking for here. F1 is 50 newtons. And F2 is 25 newtons. Right, Megan? F2 is 25 newtons? Negative 25. Good. Negative 25 because it's opposite direction to the left. We didn't worry about it until now, but now's the time. 50 minus 25 is 25 newtons. 25 divided by 4, take the 4 over by dividing, we get 6.25. 6.25, or, wait a second, this is 3 digits, this is 2 digits, this is 2 digits. Final answer should be, how many digits should the final answer be? Okay, so this is going to be not 6.25, rather it's going to be 6.3. You can say meters per second squared, or we now know that we can use newtons per kilogram as well. Meters per second squared or newtons per kilogram. Either one works. All right, let's take a look at the next question, number 5 then. A 1,500 kilogram car accelerates at a rate of 2 meters per second squared while being pulled by a tow truck. A 9,000 Newton force of friction opposes the motion. What's the force with which the car is being pulled? Step number 1, draw a Freebody diagram. Listen, your diagram doesn't have to show a car that looks like a car. Just draw it as a box, draw it as a circle, it doesn't matter. There's gravity acting down and there's the normal force acting up, but they cancel each other, so whatever, they're gone. It's being pulled by a tow truck. We'll assume it's being pulled to the right by the tow truck. I don't know what that force is. That's what I want to find, the force of the tow truck. But there's a 9,000 Newton force of friction that opposes the motion. I'm going to call FF 9,000 newtons. And I'm going to make it opposite to the way that it's being pulled. If it's being pulled to the right, friction's got to act to the left. Now that's all I really need to include with my Freebody diagram. I'm going to add the mass here, even though it's technically not necessary. And I'm going to add the acceleration here, even though it's technically not necessary. Just going to add those because I got to write down my givens anyways. I might as well just do it as part of my diagram. What's the next step? Look, what's the next step after I draw my diagram here? Step 2 of the 4-step recipe. Yeah, good. F net is equal to the sum of the forces. It's going to be, in this case, F1 plus FF, same as it was in the last one, right? Step 3. Anna, what's step 3? Yep. Good. MA is equal to F1 plus FF. And finally, step 4 is just put in your numbers to solve. M is 1,500 kilograms. We don't know what, we do know what A is this time. It's 2.00. F1, that's what we're looking for this time. And FF is 9,000 newtons, right? Right? Haley? Negative 9,000, right? Because if it's accelerating to the right, positive 2, then the force of friction is to the left, negative 9,000. 1,500 times 2 is 3,000. F1 subtract 9,000. Take the 9,000 over by adding, and F1 ends up being equal to 1,200 newtons. Sorry, 12,000 newtons. Which we actually want to round that. Here's 3 digits, here's 4, here's 4. Going to round it to 3 digits. Let's make it 1.20 times 10 to the 4 newtons. 1.20 times 10 to the 4. Number 6. 400-gram toy. Listen, we don't want to be in grams, we want to be in kilograms, so I don't want to forget to do that, so I'll circle it. being pulled by one child to the right, being pulled by another child to the left, and there's friction. There's three forces here. Step number one, draw a free body diagram. Gravity acts down, normal force acts up, they cancel. Done there. Now, let's say F1. F1 to the right, that's going to be 3 newtons. And we're going to say F2 is to the left. That's 1.5 newtons. So let's make that shorter here. Let's make that about half as long as F1. Which way is friction acting? Which way is our 1 Newton force of friction acting, Nick? Yeah, if we got 3 newtons to the right, 1.5 to the left, it's going to move to the right, so friction is going to act to the left. Let's call that FF, and let's draw that just a little shorter than F2. The mass of my car is 400 grams, or I'm going to make that 0.400 kilograms. Step 2. What's step 2? What's step 2? Yeah, add my forces here. F net is equal to the sum of my forces. That's going to be F2 plus FF plus F1. Should I have changed the order of that? Made it F1 plus F2 plus FF? Doesn't make any difference, right? Step 3. Evan, what's step 3?
To make it equal to F, the mass state.
Right. M times A equals F2 plus FF plus F1. M is, that's 0.400. A is, that's what we're looking for, I guess. F2 is negative 1.50. FF is 1.00. And F1 is 3.00. Is that right? Is that right? No? Haley, what's wrong? Yeah, friction needs to be a negative as well. So we get 0.400 times A is equal to, this ends up being negative 0.5. Positive 0.5. And A ends up being equal to 1.25. 1.25 meters per second squared. Yep. Do you always have to draw the arrows at the bottom? We should. When they cancel out, like I probably wouldn't zing you if you didn't draw them when they cancel out. But we should get in the habit of drawing them because they won't always cancel out. Now, you're going to have a quiz in a couple of days on Tuesday on this stuff. I gave you a practice quiz on Monday. They will cancel out on both of those, on the practice quiz and on the real quiz. I'll tell you when they don't cancel out, and I'll explain to you why they don't cancel out. But at some point, that's going to happen. We should be in the habit of drawing them so that we don't forget when it's time for them not to cancel out. We don't forget to draw them. Does that make sense? All right, I want to do one more example with you, and then we'll call it a day here. This is example number 4. Yeah, go ahead, Andrew. No, friction does not change because of surface area. Friction only depends upon the mass of the object, and it depends upon the properties of the materials. So if you have, like, say, rubber and ice versus rubber and pavement, okay, what matters is the mass of the car, and then whether it's rubber on ice or rubber on pavement. The surface area makes no difference. Okay, let's take a look at number 4 here. A 15-kilogram sled is pulled to the right by one person with a force of 100 newtons at 30 degrees above the horizontal. Then it's pulled to the left with 35 newtons. What's the acceleration of the sled? Step number 1, draw the free body diagram. Here's the sled. We're pulling it to the right here. We'll call it F1. It's 100 newtons. And the angle is 30 degrees here above the horizontal. And we have friction that's going to act to the left of 35 newtons. It's quite a bit shorter here. Let's just call that FF. It's 35.0 newtons. Now watch very carefully what I'm going to do here. Gravity is acting down. Right, we agree. Gravity acts down. Normal force acts up, right? It does. But normal force in this case is not as big as gravity. Can anybody suggest why the normal force and gravity aren't as big? Now, Amelia, go back to your question a few minutes ago here. Do we have to draw them in? They don't cancel here. Normal force and gravity don't cancel here, but they're going to almost cancel here. You see what I mean by that in a second. Okay? Later on next week, they just won't cancel, period. Why are they not equal in magnitude this time? Okay? Yes. This object is being pulled up with a y component of 100. Right? Whatever that y component is. So it's not gravity and normal force that balance. It's gravity balancing normal force and y component combined. The y components still balance, but it's not just two forces balancing. Now it's three forces balancing. Does that make sense? All right. There's an x component to this as well. We'll call it fx. So we got a funny angle here. What do you do when you have a funny angle? Yeah, box it off. Take it over to the side. You got 100 newtons. We got an x component right here. I'm going to actually call the x component fx and a y component that we're going to call fy. Now in this problem, it doesn't actually matter to me what fy is, but I can find it. Fx is going to be equal to 86.6 newtons using the cosine function, and Fy is equal to 50 newtons using the sine function. Does that make sense where I got those two numbers from? Let's box it off. And then let's go to step 2. This is more like step 1.5, right? We kind of went off to the side, did our little thing. Now we'll go back to our recipe. Step 2. Step 2, which says F net is equal to the sum of the forces. We're going to say FF plus what? Plus what? Yeah, Amelia? Sorry? No, not Fx and Fy. Fy is gone because Fy and Fn canceled each other out, right? Yep. Parker? Well, Fn and Fy combined had to, that was the upward forces, had to be equal to Fg, the downward force. Well, otherwise this wagon would move up in the air or down, right? Okay, let's assume that it doesn't. Yep. Yeah, then it's just Fx. All right, remember, it's not 100. 100's dead to us, right? We got rid of that funny angle. Look, this is effectively what we have now. F net is m times a. Now we sub our numbers in here. The mass here is 15 kilograms. The acceleration is what we're looking for here. FF is negative 35 newtons, negative because it's to the left, and FX is 86.6 newtons. All right, when you're at an angle, you never want to use that value that's at the angle. Get the x component and the y component. And as it turns out here, we don't actually need the y component for this problem. But we know we're not going to need the 100. Like we knew that when we started. We got 15 times a is equal to, this is going to be 86.6 minus 35 is 51.6. And then a is going to be equal to what? I'm going to say 3.4-ish. Is it 3.4? Meters per second squared. There's our answer. Got a little bit of homework for Monday. Worksheet number 11, the worksheet that you were working on for today, except this time you're going to do questions 7 and 8. You're going to finish that worksheet, please.